being said, I will be speaking about some integrable systems that naturally appear in physics, let's say. And my point of view is to try to understand them through a perspective of reduction. Okay, so Hamiltonian reduction usually. And while I will, for the first part of the talk, just set up some things that are known for a long time, my aim is then to just look at some natural, let's say, geometric generalization of these models and see what's happening there. And if you can get some new, interesting integrable systems. And so that's how I will, at the end, if I can manage the time, speak about a new real form of the so-called Royston-Schneider system. Okay, so first, let's start with something in some way easy to understand. So the Kerr-Germoso-Sutherland model. So the thing here to just note is that you should think about a system of particles lying on a circle, okay, in the real case, and the positions along the circle are just moving according to some interaction, which depends on the distance between your different particles. Okay, and so when you see at the second order ODE, you think that it looks extremely nasty and you will never be able to solve that. Having a Poisson perspective and trying to rewrite that in terms of a Hamiltonian function, well, we considerably reduce and improve the way to solve our system. Okay, so in terms of a Hamiltonian function that is in some way, let's say, physically nice because it has a kinetic term and a potential term, you see that your equation of motion are already maybe better to understand. And so my perspective here is just to recall an old result that is asking the question, what is the phase space for this model? Because intuitively you could think, okay, I have particles along a circle, so basically for my position I have S1 to the n as a space, and then I'm just taking the cotangent space to that. This should be a reasonable thing to be the phase space. But what is happening is that you can do the same kind of picture in the complex case. And for example, in the complex case, things can be nasty because you can have collisions happening, in which case, well, it no longer makes sense to use these coordinates because you will have singularities appearing. So you need to understand your model in a different way. And that's where the geometry is very important to have. Okay, so the approach that I'm following, as I was saying, is something very old, so it's due to Kashdan, Costan, and Sternberg. And I will describe here first the real case, but the complex case is basically more or less the same. And so to understand our system as just being the Hamiltonian reduction of something, we start with a very easy model, just the cotangent space to unitary matrices, okay? And that I will trivialize by just having a little g, which is a unitary matrix, and then my j, which is in the Lie algebra. Okay, so after identifying it with its dual.
Can I ask one question?
Yes.
So, in the perspective of original the system, what does this UN represent?
Sorry.
You just introduced UN.
Yes.
Ad hoc. But there must be some role of this UN play in the original system.
Well, to be honest, I don't know how they guess that you should start with this thing. Maybe.
But how is it if you just say that your exponential of coordinates, so they are elements of the maximal torus, or I don't know, very naively.
Yeah, okay, yes, that may be the best way to see that. So that in some way, you can always diagonal this G matrix, okay? And then diagonalize, you could call this diagonal entry EI to the QJ. And so that's how, okay, maybe intuitively you would think that it's good to play with that, with some UN action on your space. Yeah, yes, that's the natural thing to do. Yes, thank you. Okay. So now that we have our space, so there is a UN action on it, a natural one, and it admits it's a cotangent space. There is also a Poisson bracket, and those admit a moment map, okay, which is written like this in my trivialization. Okay, and so what we will do, okay, to make our Hamiltonian reduction is just fix our moment map to be equal to some multiple of the identity plus a rank 1 matrix. Okay. And the point of view that I want to take for my later generalization is to think of this rank 1 matrix in some way as being part of the data. Okay. But as
you annex by...
so UN will, on this model, is just acting by regular conjugation of the two matrices. Yes. Yeah. Yeah. And so I have this slice in my space, and then I'm just reducing with that UN action by simultaneous conjugation, thank you, and I get my reduced space. And on that reduced space, in fact, I can draw the coordinates from the previous slide. Okay. So as I was mentioning earlier, because of the action, you can diagonalize this G matrix. You just call the eigenvalue EI to some QJ being later the position of our model. And then with this moment map equation, you can basically just determine what is the J matrix. Okay, it will have some free diagonal entries, so you just call them IPJ, for example. And then with that moment map equation, you can determine the off-diagonal entries. And what you will be able to get then is that the trace of the square of that matrix up to some sign will be exactly this Hamiltonian that I've written there. Okay. And what is more is that you can easily form an integrable system from this function up to taking the imaginary part when they are imaginary. Because basically all these J matrices, they are just in the fiber, so you know naturally that they commute. Okay, so it's extremely easy to know that these things will be commuting, and by reduction, because these are invariant functions, they are still commuting on the reduced space. Okay, and by a very easy counting, you know that you have half the dimension of your space functions that are commuting, okay, because this reduced space has just dimension 2n. Okay, so my qi and pj coordinates are just coordinates on this whole space. Okay. And what is nice with this perspective is that you can easily pass to the complex case. You just replace everywhere your unitary group by GLN. Okay, but then okay, that's where the things are getting maybe nasty or very interesting. Is that you can no longer diagonalize any matrix in GLN. Okay, so you will have this kind of singularities that can happen where the particles may collide in the model. Okay. So this is for the first interesting model. And what I will be looking at are so-called spin generalizations. Well, oh, yes?
Do these people look at the rational version, or do they actually do the trigonometric as well?
They did both. So, so the so-called rational version of this model, if you don't know it, is that you start with the cotangent space of the Lie algebra of UN. You do the same thing. And then what's happening is that you can do the same thing, but here basically your potential will be in 1 over the distance squared. Okay, so that's why it's called rational instead of trigonometric, because you have a rational function instead of the trigonometric one. Okay, and that's when you start with the Lie algebra instead. But yeah, they do both in the paper.
Not in Wilson's paper.
And yes, Wilson just do the rational case, but basically, because going from the Lie algebra of GLN to GN just require inverting a matrix, you can get the same story from his paper. You just require everything to be with an invertible matrix. Okay. Right. So let me now turn to so-called spin extensions. Okay, so the slide looks extremely ugly, so let's try first to just look at what could be a generalization here. So if you remember, at the level of equation of motion, what I had earlier was that the second derivative of my position was just a sum of a constant times, well, so some term here happening. And what I'm doing here in this spin generalization is that I'm adding some new variables here, okay? And these new variables are linked from what? From some extra variables here that I'm calling AI alpha and BI alpha, which are some vectors and covectors that you associate with any of these particles. Okay. And so in particular, these Fij that I'm introducing, they are just taking the vector, the yes, the vector associated with the ice particle, with the covector associated with the j's particle, you pair them together, you have something, okay? And then, modulo some extra reduction, you have a big space on which you can write these equations of motion. So again, if you just look at these equations, it looks a bit terrible, okay? But the point is, again, from a Hamiltonian perspective, you can write them extremely easily in terms of this Hamiltonian function here, okay? And again, everything is really nice. So as before, my Qi and Pi are canonically conjugate, and this is the same of these extra new variables that we are associating, okay?
So you want to regard the H spin as a function of Qi's and Phi's?
That's a good question. So these spins are not function of the Qi and the Pi. So these are really new independent variables, okay? And okay, there are some constraints coming from some S and S1 actions in addition, but that's not very important here. Okay. So yes, at the moment these variables are really independent. Okay.
This H spin is a function of that.
Oh yes, but the Hamiltonian, yes, it's a function of all these different variables, right? Yes. So these new added spin variables that are appearing here in the potential term instead of having a constant over sine squared. We now have these new things that are appearing. Right. Okay. So yes, this looks a bit weird the first time you see it, but again, geometrically, it's extremely easy to understand this generalization. Okay? Because what am I doing, in fact, compared to my previous model, is that I'm taking T star un as before, but now I'm adding d copies. So d was the number of elements in these vectors that I was associating with my particles. And so I'm adding d copies of Cn to each of my variables in some way. Okay. And so, again, I'm trivializing the cotangent space. And now what I'm doing is that I'm looking at the size of what? Well, this Cn, I can see it as a Hamiltonian, again, UN space for the left multiplication on Cn. Okay, so it has the moment map given here by just taking the vector times this complex conjugate. Okay? And so here, as a moment map for this bigger model, I'm just taking the previous moment map plus summing all these other moment maps for all the Cn copies. Okay. And then again, the story is exactly the same once you know what we did earlier. You just fix this thing equal to a multiple of the identity, and then you finish your reduction by looking at orbits there, where again G and J are conjugated while you act on the left on these vectors. Okay. And it so happens that on this reduced space, you can build an integrable system. In fact, a degenerative integrable system. Okay, because as in the previous case, you still know that these functions, the trace of the J matrix to any power, these things are Poisson commuting. That's extremely easy. And I already explained that in the previous case. But now what you can do is that this J matrix, you can in some way sandwich, you can take it to any power, sandwich it with one of these vectors multiplied on the right, the covector on the left. And you have many, many new functions that are still commuting with those. Okay, so you can build a degenerate integrable system, which again, if it's still a notion that you are not too comfortable with, means that here we have a reduced space of some dimension, 2n times d, so n the number of particles, d the number of spins. Okay, and on that space, I have some algebra of functions that are, so these things that are of dimension n, okay, so they are all Poisson commuting, and the algebra of these bigger first integrals has codimension n. Okay, so the dimension of the center and the codimension adds up to the dimension of the space, right?
Excuse me?
Yes.
Is this reduced space smooth?
Yes, yes, in this case.
Even if you have same eigenvalues, like in your J?
So this is the very nice thing here is that, yes, everything is smooth. And as you say, in this model, you could have some of the eigenvalues that are the same, but it doesn't change much. Really, you end up with something that is smooth.
But then we cannot get the original Hamiltonian because it would be singular.
Yes, so where is my Okay, let me think. Can you have, in fact, yes, does it? Okay, I said that it was always defined, but okay, I'm cheating. Yes, this is only defined when these eigenvalues are pairwise different. Okay, so it will not be defined on these other points.
If you get trace of j squared, then it does not give this one then.
So the thing is that if you write this j squared, okay, you need your moment map equation to write j. Okay, and what's happening is that, okay, maybe I will do that and then you will see what's happening. So if I'm looking at my moment map equation, when j is diagonal, I'm writing it in the ij tree as gij times 1 minus ei q. Okay, let's write at entry kj, qk minus qj is equal to, well, something which is given by this identity plus d rank 1. Okay, and so the point is that when k is equal to j, this is 0, so you cannot express, you cannot define this j on that part. Okay, but at all the other points where these are distinct, you can define your j in the way to recover the previous model. Yeah, so sorry, this was not clear when I said it earlier. Right. So one quick remark here is that this way of reducing by first adding some well, d times this space and then making it the previous reduction to get my so-called spin Kerr-Germoser system. It's slightly different to what was presented on Monday by Lotze, okay, because what he considered was in some way the Poisson-Lie version of not adding this part, but reducing at another coadjoint orbit, okay? And, well, these are also called spin Kerr-Germoser system or spin Rörsöner-Schneider system, but, well, they are geometrically reduced in a different way. Okay.
But shouldn't it be equivalent?
And so what's happening is that at the level of equation of motion, in those other spin generalization, well, you don't have the decoupling in terms of the A and B matrices, but you still have these F that appear, and these F are really so the matrix Fij, it's the matrix of the coadjoint orbit that we're choosing.
But now you chose that vector, and doesn't it define for you one of the coadjoint orbits if you just put your vector, the contribution of the vector from the left-hand side to the right-hand side?
So what you need to do to define a coadjoint orbit would be to say, for example, that you need some extra reduction, yes, to be able to define a coadjoint orbit. But what is more general here is that I can take the D to be as big as I want, so maybe bigger than n the dimension of my matrices. And so it's more general in some way.
But in principle, many of those cases would be equivalent to coadjoint orbits.
Many of those cases can be reduced to the coadjoint orbits case by just fixing things. So, okay, so this was for the Kerr-Germoser version, and what I want to talk about today is a generalization of that which is called Rörsöner-Schneider version. So then I will not be really able to write on the Hamiltonian numerals and the equations of motion in general because they look more difficult. So just to give you an idea, what's happening in this picture in the Rörsöner-Schneider version is that now you have some Hamiltonian function which depends as exponential of your momenta. Okay. And so it can no longer be broken as some a kinetic part and some potential part. In some way, everything is mixed together. Okay. And here, really, it's starting to be also interesting because the complex and real models are very different. So, for example, this is the Hamiltonian in the complex case, okay, but in the real case, you cannot write it. So there are some square root involved, and it's a bit more complicated than that. Okay. So the question is then, there are these obvious generalizations from a mathematical physics point of view. Can you geometrically understand those as being some reduction of something? Okay. And so I will start by recalling what is known without spin variables, okay? And then I will add some spins, as in the previous case, which was adding some vectors and covectors. And in the end, I will talk about something new. Hopefully I will have time for that. Right, so what is known about this Royston-Schneider system in general is, well, because this should be seen as some, let's say, multiplicative version of the Cauchy-Moser case, you would expect that your reduction is some multiplicative version of reducing the cotangent space. So it's, in some way, philosophically really normal that you should expect to either do some Hamiltonian reduction using Poisson-Lie groups to get this generalization, or doing some quasi-Hamiltonian reduction. So I will mostly be focusing on what it means to be a quasi-Hamiltonian reduction later on. Okay? The only thing that I want to say is that, well, this Poisson-Lie point of view, it's really what was in Lotz's talk on Monday. But he was doing this coadjoint orbit spin version. But I mean, apart from that, it's really the idea that we had. But what I want to say, rather, is also that there are things that are different between the 2 points of view. Okay? So if you look at the complex version of this Royston-Schneider system, and you do either the Hamiltonian reduction using Poisson-Lie group or the quasi-Poisson reduction, then what's happening is that basically you get the same phase space when you have no spin variables. Okay? You get exactly the same thing. But what is already very interesting in that, in the real case, if you take the two different perspectives, you get different things. Okay, so in one case you have a compact space, in another case you have a non-compact one. So it seems to be that the two techniques will give you different real forms of the same complex space. So from this point of view, it seems interesting to just try to understand all these different techniques and see what's happening with spin variables later on. But okay, first let me just recall a bit what it means to do this quasi-reduction, if you don't know what it is. So the general idea, so first without spin, without adding any kind of vectors and covectors in addition. The general idea, if you don't know that, is that you start with 2 copies of your group. Okay, so in the real case, you take 2 copies of UN. In the complex case, 2 copies of GL and C. Okay. Then, on this place, you can act by simultaneous conjugation. Okay? And because of this action, you can define naturally a trivector on your double. Okay? And then you have what is called a quasi-Poisson bracket, which is almost a Poisson bracket, if you don't know that, but it has some failure to satisfy Jacobi identity, which is completely determined by the trivector coming from the action of the group on itself. Okay. The important thing is that this failure, because it's coming from the action on the group, okay, this failure completely disappears when you are considering invariant functions. Okay. So it means that when you will perform reduction and will be working with invariant functions, everything will be like in the Poisson case. Okay, right, so you have an action by, this action is compatible with the quasi-Poisson bracket. And finally, as in the usual case, you have some notion of moment map. The only difference is that now it's group value, so it's in the group, not in the dual of the Lie algebra. But apart from that, it's really the same story. And yes, okay, obviously I should say that, I will be mostly focusing on the quasi-Poisson point of view, okay, which follows Alexeyev, Kosman, Schwarzbach, and Mein-Ranken. But in fact, all the spaces that I will consider have a corresponding 2 forms, okay, which is, again, like symplectic, but it has some failure to be symplectic. And this is the approach of Alexeyev, Mike, and Mein-Ranken, and that Philip Bosch has explained in the complex case, okay, because I will be considering the 2 approaches. Right, so what is the general idea of what you do with all the spin variables first? Oh, sorry, I should have done a bit more. With all the spin variables first, but that we will mimic later on, is that you will, as before, just take the pre-image of your moment map of something which is like of minimal dimension. So remember I was talking about some multiple of the identity plus rank 1 condition. So we will still be doing that. We will require that this group valued moment map is taking a value now in the corresponding conjugacy class rather than a coadjoint orbit. But again, after you fix that, you just consider the orbit there, and provided that you've taken a generic conjugate C-class of that form, it will be a smooth space. And then you can define under some integrable system, which has nice local coordinates that allows you to have the interpretation as a Royston-Schneider system. So this is the general idea. And so now what I want to emphasize is, why is this reduction picture interesting? Because basically it gives you explicit flows before reduction extremely nicely. Okay? So what is happening, if you remember in the previous cotangent space case, is that you were interested in function of the form trace of one of the matrices to any power. These were Poisson commuting. Here, the idea is still the same. So our quasi-Poisson double has 2 copies of the group. You just take 1 copy, and you take any invariant function of that copy. Okay. And this thing will be naturally Poisson commuting. Okay, because your quasi-Poisson bracket satisfies Jacobi identity on these invariant functions. And so, in fact, all these invariant functions will descend to your reduced space and define an integrable system there. And what is nice is that you can very easily just integrate everything before reduction. So if you've never seen that before, if you take some easy cases, like just take the real part of the trace of the matrix you've chosen or the imaginary part, the equations of motion are like this. So the matrix chosen will evolve constantly. The other matrix will be evolving with an exponential of the constant matrix. Okay, so this is extremely easy to write down, and you can do that for an invariant function. Right, so this is from my point of view why having always a reduction picture is nice, because then you can project your flows on your reduced manifold, and while you may have very, very cumbersome equations, ODEs defining your equations of motion, before reduction, when you can understand that reduction picture, before reduction, it's almost trivial to do. Okay. Right. So this was for the Royston-Schneider case without spins. So what is happening with spin variables? Well,
Excuse me, the previous slide. How did you check that you have the right dimension for it to be completely integrable?
all right, so usually this is the hard part, right? But here the point is that, so this space Cn will have dimension 2 times n, okay? And this H, well, basically you can take the real and imaginary part of any of the trace of any power of your A matrix. Okay, so your A matrix, it's a unitary matrix, so it's diagonalizable. And so basically you are considering an invariant function of the eigenvalues of your matrix. So you will have n of them at a generic point.
So generic means?
So at a point where the eigenvalues are pairwise distinct again, yes. And so well, maybe that's a good point to say that because you see that things are not nice when the eigenvalues are the same, you can determine that your integrable system is well, you have the independence explicitly at those points where the eigenvalues are distinct. Okay, so this is something that you can really control. Okay, right, and so, well, I mean, I will skip that, but the point is that there exists a spin generalization of this model. Okay, so again, at the level of, in some way, reduced equations of motion that you can write down locally. And the point is that, well, you can ask yourself the question, is it a reduction picture for these equations of motion? And what is quite fun is that these equations of motion were first written, in '95 by Khrushchev and Zabrodin. But in some way, you don't, I mean, in their paper, you don't have the Poisson structure defining these equations of motion. Okay? So they can still show that there is an integrable system there, but in some way, the Poisson structure is completely hidden. Okay, so a nice question, if you can get a geometric reduction of this system, is also to say, well, can you determine what are the Poisson bracket between all these coordinates that may appear? Okay. Right, and so what I want to say is just, well, the different approaches that exist in this spin case. So as you can see, the years are really recent. So these things were written down in '95, and the reduction of the system was just like less than 5 years ago. Okay? So the point is not that it's that difficult to get those, but you need to understand what to do in order to be able to derive these equations of motion. So just a little historical thing. So I started during my PhD obtaining the quasi-Poisson reduction of the complex case with my supervisor, then Oleg Chalik. Okay, and then a few months later, there was the Poisson-Lie case which was obtained, and again, you get basically the same phase space. Okay. But what is more interesting is that then we went to the real case with Laszlo and Jan Marshall. Okay, and very recently, and I will finish by that, we got another real form by quasi-Poisson reduction. Okay? And the small thing that I want to emphasize, and that I will say again later, is that in this spin case, while before without spins, the real case, you could distinguish the two by having one space which was compact, the other one being non-compact. In these spin generalization, both spaces will be non-compact. Okay? But they will still be very distinct. Okay. Okay. So first, yes, I will just quickly give you an idea of what's happening in that case, and then tell you again about the geometric reduction of the real case. So how do you get this quasi-Hamiltonian point of view in the complex case? So again, first we start by something which is like what we had previously. So previously we had cotangent space to UN or GLN, which is replaced now by this orange bit, the quasi-Poisson double of GLN. Okay. And then previously what we were doing is adding a bunch of vectors. Okay. And these vectors, so I wrote them Cn in the real case, which was like T stars Rn. And so in the complex case, you want something that will be like T star of the base field to the power n, and you take a bunch of those. Okay, so your master space, just geometrically, it seems sensitive to use that. Okay. But now the point is that on a dense subset, open subset of these cotangent space to Cn, there is in fact a quasi-Poisson structure. Okay, that I use following some convention of Vandenberg, but it was in fact written in a very different way by Philippe a bit earlier than that, I think. Yeah. And the point is that once you know what this extra bit is, then again, the reduction is really the same as what you had earlier. So you have here the moment map, well, this Lie group valued moment map for the quasi-Poisson double. Okay. And then here you just take the product with the moment map corresponding to these extra bits that you've added. Okay. So again, it's similar to what we had earlier, where we were taking the moment map of the cotangent space and adding the moment map of all these extra vector spaces. Here it's just that we multiply things because we are in the quasi-Poisson case. And then again, we take the reduction of that at a multiple of the identity value. And here there is a small condition that you need in order to end up with a smooth space after reduction. Okay, so here the GLN action is by simultaneous conjugation on the two copies of GLN, and then left and right multiplication on the vector and covectors that you've added. But under this action, okay, you get a smooth space, provided that your eigenvalue gamma are not primitive roots of unity for any k between 1 and n. Okay, so the general idea to understand this condition is that you don't want a solution to when you remove the blue bit here. Okay, so you don't want to be able to write down a solution to this thing.
Why do you write it as T star Cn? You're not using the symplectic structure on T star Cn.
No, it's just for the presentation. I thought it was nice. And okay, and maybe to motivate what we will do in the real case, it's because it's not an exponentiation of T star Cn, but I mean up to making some local changes, it can be put in that form. Okay. So in the real case, we will really be exponentiating T star Rn. Okay. But so once you have this general reduction picture, you can then, on some open subset, just diagonalize one of your two matrices in GLN, just use that to write down some local coordinates, be able to identify with this spin trigonometric Royston-Schneider system, be very happy with that. So it's really nice. But so now my point is more to say, okay, what would be the equivalent of that diagram in the real case? Yeah. So this is a recent work with Laszlo Fairon. And so what we had to do basically is to understand, well, what would be the kind of extra bit here that you need to add to your quasi-Poisson double of UN, and which would be like, okay, some tangent space of some vector space to any dimension. And so, well, I mean, we spent a few months on that, mostly because I was stubborn. I really wanted to start with a quasi-Poisson bracket and try to see what I was able to do. But the idea is that if you look at the theory of these quasi-Poisson spaces and so on, there is an exponentiation procedure that allows you to start with a Hamiltonian space, okay, in the usual Poisson setting, okay, and then end up using that exponentiation picture with a quasi-Poisson space. Okay. And so it so happens that when you start with the Hamiltonian space T star Rn, so again, that's what we were adding in the very first part when we were extending the cotangent space to UN. When you start with that, exponentiate, then what you will get is, well, almost Cn, but there are some invertibility conditions that will necessitate that you work, in fact, on an open ball around the origin. Okay. But the good thing is that this exponentiation procedure, it's extremely explicit, so you can explicitly write down the quasi-Poisson bracket, which takes this form, and which, in my opinion, is nice. Okay, so as you can see, if you forget about the extra thing here, the extra bit that we are kind of adding, it's really just your usual Hamiltonian Poisson structure on T star Rn. But now, because you are in a quasi-Poisson space, in the quasi-Poisson case, there is an extra thing happening here. Yes?
How is it, this bracket, would it have singularities somewhere, or they agree to?
Yes, so good question, thank you. So I'm restricting to that disk. Why am I doing that? Well, because if you look here, there is an extra function that is appearing, and this function, well, basically it will be analytic, well, on that disk up to changing this t by x t squared, okay, or in fact any corresponding annuli. Okay, and so you could take this disk as we will be doing, or any such annulus, okay, and do that same procedure. But yes, there will be some singularities appearing, and you need to discard them. Right. And so yes, and maybe the key remark to motivate this exponentiation name is really that you just get, as a Lie group valued moment map, the exponential of what was your earlier moment map. Okay. But provided that you have that thing, then what's happening? Well, you just play again the same game. Okay, so you start with your quasi-Poisson double. Okay. You add these extra bits that you've identified. Okay, and here we are being a bit fancy because we want to. We take disks of different size. But really, up to rescaling, there is basically almost just one case where you just put all these, in some way, radius equal to 1. Okay. And then what you do, well, you do, again, the quasi-Hamiltonian reduction at a multiple of the identity. So again, in that picture, you have here your Lie group valued moment map for the quasi-Poisson double. Here you have this product of exponential of the moment maps in the Poisson case, which now becomes moment maps in the quasi-Poisson case. You impose this relation, and then you do the reduction. And so, I mean, if you agree that the previous diagrams were all of the same shape and making sense, you would say, okay, this reduced space is really where the integrable system must be living, this generalization that I'm considering. So this should be the normal thing to do. Okay. So really, conjecturally, this is where our integrable system lives. The kind of problem that we had is that in some way, we can easily construct a Poisson commuting function, and in fact, a conjectural degenerate integrable system. We know all the first integrals and so on. But the problem for us now is that we don't know nice local coordinates there. So at the moment, we cannot count the number of functions that we have to really claim that there is an integrable system down there. Okay. So I will need to do something else in order to, well, get something. Okay, so before talking about the integrable system point of view, let me just say this important thing that I mentioned earlier. So these spaces are non-compact when the number of spins in some way are greater than 1. Okay, and I mean, okay, we didn't really think about that in the first place, so we were expecting something compact. But once you know what to do, it's obvious that it should be non-compact. Okay, so just to draw you a proof of what's happening. Okay, so this is your moment map equation here. And as I was saying, so you have your quasi-Poisson double, which has some, which is parameterized by matrices A and B. And then I said, okay, you are adding to that a bunch of disks of the different radius. Okay. And the idea is the following. So let's assume that up to taking the V alpha equal to 0 in all the disk after alpha is equal to 2, that you have just 2 disks. Okay. And then what you do is the following. So in the second disk, you just take a family of vectors that will go towards the boundary. Okay. So all my okay, I'm sorry. I should say I'm still saying disks because I'm using D, but these are balls. Okay. But so you just take a family of these vectors V2 that are going to the boundary, but I haven't opened this, so I mean it will not be in the space in the limit. And then what's happening is that when you put that on the right-hand side, this exponential of I x alpha of any of these things on the right-hand side, you end up with something which is just a unitary matrix. Okay. So now the second thing that you do is that for any such point, you can find a point in the first disk which allows you to say that this product here times this exponential I gamma is in SUN, okay? So basically you just use this disk to rescale the eigenvalue, okay? And then the last trick is just to know that whenever you have two matrices AB in well, in UN, or in fact in SUN, you can find them such that the commutator is equal to an element in SUN. Okay? And so by doing that, you have a family of points which will, in the second disk, just leave your space. Okay? And so you can show then that this will be non-compact. So this was a very nice trick, extremely easy to explain, but that we didn't think about. Okay, right. So to start finishing my talk, I just want to say that, okay, we can prove also smoothness. It's very easy. When, again, we have this condition that we are not reducing a multiple of a primitive root of unity. And also we can, even if we are not able to really write down local coordinates on that reduced space, we can take a covering of it such that some complex Hamiltonian induces the correct equations of motion. So this is why we, in some way, our belief that this is the right space to consider, I mean, it is true, even though we don't have an integrable system yet. Okay, so what about integrability? So as I was saying, we cannot yet show that we have an integrable system there, but can we show something else? So we have this commuting function obtained by taking an invariant function of one of the matrix. Okay, And then what you can do, okay, and here I will, well, just say that very quickly because this is more or less the same idea of what was presented in Loss's talk on Monday. So what you do is just you write the following map psi, which is basically a map of invariant functions. Okay, so any elements appearing there, it's constant under the flows induced by these invariant function of the of the first copy of UN. Okay. And so when you consider all these functions, you can say that you have a kind of degenerate integrable system on your quasi-Poisson manifold. Okay, so in some sense this is not Poisson, but you have a similar notion that can be written down. And then the whole point is that you can reduce this degenerate integrable system to another degenerate integrable system once you take the quotient of the whole space in some way by this UN action. Okay. So the slide that I was interested in, it just fits in there. Okay, we cannot prove integrability there, but on some open subset of this stratified manifold, okay, we have a degenerate integrable system. Okay. And the point is just that in some way you project whatever was your degenerate integrable system before reduction there. And so the last thing that you can ask yourself, and again, it's very similar to the Poisson case that was explained on Monday, you can ask yourself, can you restrict to symplectic leaves in that stratified space? Because the symplectic leaves will really be obtained by fixing the value of your moment map. And to finish, I want to say that in some cases it's working. So basically, when you are fixing the invariant function of your moment map, which becomes Casimir in that space, you get an integrable system there. Okay, well, okay, I should say, when you fix this invariant function such that you have a regular conjugacy class in UN, okay, but in the space that we are interested in, this is still not working. Okay, so to conclude, we kind of conjecturally very strong proof that we have, in some way, the correct phase space to claim that we have a new real form of this spin-Rosner-Schneider system, but we are like modular counting, not able to get that. Okay, so thank you all for your attention.